for stimulating discussion. And this is probably a question comment for Richard and probably Alexei Starobinsky, if Alexei is still here, but of course also to others. This is about the sitter. So for some time, several years ago, starting, I've been arguing together with my collaborators that because in S-matrix theory of gravity, such as string theory, okay, the sitter cannot be a vacuum because you cannot define the sitter as matrix in the sitter. There are good reasons for it. I will not enter there. Therefore, the sitter has to be considered as an excited state built on top of valid S-matrix vacuum, such as Minkowski. Okay,
yeah.
So that's my.
Gia, what would you say to the construction that, let's see, Mark Shrednicki, Merolf, and Morrison gave of an S-matrix for massive scalar field theory?
No, massive scalar field, there is no problem. I explained it in my paper very clearly. The problem is gravity. You can
so you mean for gravity, there's no
exactly.
S-matrix.
That's exactly the point. Yes, thanks. So that's exactly the point. So I think what happened is that because of this intuition that for other spins, such as a scalar field or a QCD, we can construct at least approximately, at least asymptotically valid S-matrix description in the sitter. I think this was not paid attention to gravitational part. And what I have shown is that there is no way to do that for quantum gravity. In other words, you can construct this, you can think of the sitter as a vacuum for any other S-matrix construction, but in that limit where the sitter becomes a valid vacuum, quantum gravity decouples. So closed string, at the same time, closed strings decouple. So there's trivializes. So closed strings have no S-matrix, and this is very important. So that's precisely the point. It's really issue is quantum gravitational, and therefore, what's the way out? So therefore, the only way out that I see is that the sitter should be considered as an excited state, some sort of a coherent state. For example, a coherent state constructed on top of the Minkowski vacuum or valid S-matrix vacuum. And now, once you adopt this picture, it turns out something very interesting happens because now the sitter is a state, it's no longer a vacuum. And for example, you can recover all properties that we know about the sitter in semi-classical limit, but only as a limit. Okay, so they are only valid for a finite time, and after finite time, which we call quantum break time, the sitter fully departs from semi-classical approximation. And that's deadly for the sitter. So this means that the sitter necessarily should have a graceful exit, should find a graceful exit before the quantum break time. And so this I think this thing is very important for complementing, in a sense, your picture or completing it, because the way I see it is that, so first of all, I fully agree that something is happening in the sitter and quantum corrections must be taken into account. But at the same time, what I see is that precisely at long time scales, the sitter, approximating the sitter as a vacuum is no longer valid. So therefore, what I see that your computation must be completed by taking into account that the sitter is not a vacuum really, okay, in order to draw a correct conclusion. So that is my point. So therefore, in certain sense, considering the sitter as a vacuum and computing corrections to it, to gravitons, let's say, etc., is like cherry picking. So it's not a consistent picture, because you're saying, okay, here are quantum corrections, they must be taken into account, but precisely the point that those quantum corrections are important on long time scales, that's precisely what invalidates the sitter as a vacuum. And so therefore, I think this is a very important point and is not enough appreciated. And for example, one of the consequences of this point is that in quantum gravity, which is defined through S-matrix, cosmological constant cannot be part of the energy budget of the universe. It's just simply impossible, because quantum breaking is incompatible with cosmological constant. So whatever is there cannot be a constant.
Yeah, I don't disagree with what you're saying, but you know that we're a tiny minority of the people who work in this field. The orthodox opinion is that there is zero I mean mathematically zero back reaction.
I don't think that's. I mean, that is very easy to to argue against. I mean, that's obvious that there is never a zero back reaction in any system in nature. I mean,
well, I think it's true that there's not zero back reaction, but if you know a way to convince the physics community of this without doing some pretty hard calculations, please tell me. I mean,
you know, that's a fair point. Probably that's a fair point. But look, my task here is not to convince someone. I want to be convinced myself first. And in order to be convinced, I think we have to do a fully fledged computation and at least, okay, convince each other first. And what I'm saying is that this computation, there is a big part which is important in order to take into account that the sitter is not a vacuum. And that's a very important part for getting a correct answer, what is happening in the sitter. That was my point.
Well, I'd like to just see, I'd like to get people to the point where they agree that the corrections in de Sitter, if you did, look, I agree with what you're saying. I'd like to get people to just accept that if you started in de Sitter and then computed perturbative corrections, they would get non-perturbatively large. That is not agreed to at all. Absolutely.
No, sure,
I'm sure that if you did a poll of the people who allege that they work in quantum gravity, the majority, and indeed the overwhelming majority, would argue that it is zero. Now that seems to be lunatic nonsense to me, but that is the opinion. So it seems to me that that's what's got to be addressed first.
In any case, I mean, my point was about physics. It was not really about, I mean, I didn't make those polls and I don't know what really people think. I cannot really claim that, but my point was physics point.
See, I know it because I get that response every time I submit a paper, every time I give a talk, every time I submit a grant proposal. And I know it intimately that they do believe this. They really do believe that it's mathematically zero. Again, I think that's nonsense. Now, you raise an interesting question. How would you do a calculation to see the evolving geometry? And
well, I did it. So that's my point. So I mean,
really,
at the end of the day,
show me how to do it.
I think Robert also has something to say about the computational part, right, Robert? You were mentioning something in the chat.
Yeah, but
that's right. So I'd like
I just wanted to finish my just one microsecond.
Okay.
So what I want to say is the point. I mean, at the end of the day, there is one truth, right? So there is one truth, and we are trying to get to it, and we are trying to get to it from different sides. And I'm what I wanted to share. I wanted to share my side because I think that my side of the story is very powerful because it's based on the S-matrix approach. And S-matrix approach is defining for quantum gravity theories such as string theory. So therefore, I think I have an extremely strong argument that the sitter cannot be a vacuum, at least in those S-matrix theories. And therefore, it has to be an excited state. And there are certain generic features that we have found by doing computations in treating de Sitter as an excited state. And one of these features is quantum break time. By the way, de Sitter also comes out to be a saturated state, very similar to black hole in this case. And it exhibits this quantum break time. So this was my point. I wanted to just say that sometimes it's useful to look at the same problem from different sides. And then, sorry, yeah.
Yes, I completely agree with what you just said, Gia. And in fact, I think there's a very close relationship between your approach and Richard's approach. So I think if you go to the quantum break time, I think Richard will find that that's the time when the back reaction terms become large and the perturbation theory will break down. So I think there's a very close relationship between what you are doing here and what Richard and others are doing.
In other words,
I think I told you about this in person already.
Yeah, I agree. But what I'm saying is that what I'm doing is precisely will help to answer what happens after quantum break time.
That's right.
Because that's precisely my point. Because you see, there are certain questions that can only be addressed within a microscopic theory. That's the way nature works. If we don't have microscopic theory, sometimes we cannot even pose those questions. If I give you a bucket of water and water evaporates, you need to have some microscopic theory to understand why that happens. Otherwise, you cannot even ask the question, what is the back reaction, why, and so on. And my point is that exactly the same is true for de Sitter, for a black hole, for any other system of nature. So we need a microscopic theory, and then we can only pose those questions within this type of microscopic theory. And this microscopic theory, yeah, that's what precisely was my point, what you said. But I'm saying it is more powerful because it allows to resolve de Sitter as a coherent state, a substructure. So I'm not assuming that de Sitter is a vacuum, and therefore it allows to see more and to see more distant future than quantum break time. That was my point, and I think that is
yeah. I'm not sure what significance you ascribe to a vacuum. When Nick and I, you know, my colleague Nick, who attended your
of course, yeah, sure.
Nick, when we do calculations, what we do is to just do perturbation theory around de Sitter. We're capable of doing perturbation.
That's what I mean vacuum. So you are not resolving what this de Sitter is made of. And what I'm saying is that if you think of de Sitter as a coherent
what are you talking about? I mean, in general relativity, it's made of a cosmological constant, right?
No, that's my point, because that's not the picture of S matrix. That's precisely the picture that has to be fundamentally changed, because if you think of de Sitter as being made out of cosmological constant, you are bound to treat it as a vacuum. And once you treat it as a vacuum, you are out of the, you have derailed, because
let me see, by vacuum, you mean a background field configuration, right?
Right.
Is that what you mean?
That's right.
But what's wrong with that?
Because there are certain back reaction effects that cannot be taken into account unless you know what is the constituency of that object, right? If I give you, let's say I give you a classical field configuration, okay? For example, a laser pulse. I give you a laser pulse. Laser pulse is a classical field configuration. Now I can do physics of quantum charges on the background of classical laser pulse. I can do it, no problem. But if I want to understand 1/n effects on de Sitter, on the laser pulse, because laser pulse is a coherent state of photons. If I treat it as a classical field, I'm missing that information. This is a fundamentally new information that is there in the corpuscular picture. So you need to resolve it corpuscularly to understand 1/n effects. So basically.
So are you saying we get different results if we did the calculation in a different theory where the thing that was giving the approximate de Sitter phase was not a bare cosmological constant?
Approximate de Sitter phase, the calculations diverge after quantum break time. So after quantum break time, the one picture simply cannot address it, because we are
okay, but I don't disagree. We need a way of non-perturbative.
I have it. That's what I'm saying. I have way because I'm resolving de Sitter as a coherent state. I'm saying de Sitter is not a dead classical field configuration. It's a quantum coherent state of gravitons constructed on top of.
We don't think it is either. What's wrong with just solving the effective field equations?
No, sometimes things are simply enormously simplified if we go into a corpuscular picture. Of course, if you are infinitely powerful.
What does that mean? Yeah, I'm not sure I understand what that means.
It means the following. If you are infinitely powerful, right?
Yes, okay.
If you are infinitely powerful, and for example, you can resum, so you compute corrections to de Sitter. At some point, you see that the perturbation theory breaks down. At that point, if you are infinitely powerful, you can resum probably all the series, take into account non-perturbative effects, do some resurgence or something like that, and recover finally some correct answer. I'm saying I'm not infinitely powerful, and I don't think anyone is, and therefore there is a shortcut. In order to understand what this back reaction is about, I'm doing a shortcut. I'm saying, look, I know what is the back reaction about, because de Sitter doesn't have an infinite capacity. It's not an infinite capacity classical field. It's a coherent state made out of finite occupation number of gravitons. And therefore, back reaction I can take into account in that way. And that's a shortcut, and that's an enormous simplification. That's what I'm saying. At the end of the day, physics is about trying shortcuts and right language for getting to the answer. As fast as possible, right? That's what I'm saying.
I'm happy to try almost anything that gets you out of year-long calculations. I don't really understand what you're saying, though. I'm struggling to understand it. Suppose, so the theory that you want to do is not general relativity with a positive cosmological constant, it's something else. What else?
Because it's a general relativity with zero cosmological constant, because the general relativity with positive cosmological constant, such theory as an S-matrix theory doesn't exist. That's why in string theory, despite the fact that there was an enormous effort we undertook to find
I'm not sure I understand why it's necessary that every theory be an S-matrix theory. I do lots of calculations. I don't do it with S-matrix.
No, that's a different. No, that's a separate discussion. No, that's a separate discussion.
Functions.
Sorry. I think Andre want to say something too, right?
That's a separate discussion. I'm not.
Andre, please.
For me,
Yeah. You were writing a lot in the chat. Yeah.
I think that in this debate between Richard and Gia, I would better side with Richard, because you see,
I could tell that. Yeah.
What really Gia understands under vacuum, de Sitter is vacuum. What do you mean? De Sitter is just a mean value.
You want me to give a talk?
Quantum metric observable.
You want me to give a talk? You want me to give a talk? So okay, let me explain. Let me try to explain. I will not give a talk in 2 words. Look, so there is a particle physics way of understanding gravity, and string theory belongs to that particle physics way of understanding gravity. And there is general relativity way of thinking about gravity. Now, for somebody coming from general relativity, there is no difference, the fundamental difference between de Sitter and Minkowski. They are both backgrounds, a classical background. There are infinite number of classical backgrounds that you can consider in GR, and you can do physics semi-classically on top of those backgrounds. For someone coming from a particle physics theory, the only definition of quantum gravity we have in form of string theory is an S-matrix theory. There is no other formulation of theory even. So theory is not formulated through the Lagrangian, it's not formulated through world identities.
Why?
It's formulated because that's the state of art. I didn't invent string theory.
No, the state of art is path integral, and path integral does not necessarily serve for the construction of S-matrix. You just can calculate some amplitude.
Andre, let's not debate about textbooks material. Okay, so the string theory is formulated as an S-matrix theory. There is no other formulation of string theory existing at the moment. Okay, I'm taking this as my starting point. I don't want to debate my starting point. That is a textbook material.
Why do we need to start with string theory?
Of string theory?
No, you don't.
Why necessarily string theory?
Because I'm starting from string theory, because that's the. Look, we are always doing calculations where we can. Okay,
but how can it be different than gravity considered, general relativity considered as a low energy effective field theory? I don't understand.
Sure, that's the same. I mean, I can take the limit. I'm saying that I'm working in an S-matrix theory of gravity. Now, I don't have to mention string theory. If you, that's fine with me. If you don't want to mention string theory, let's not mention string theory. But I'm working. My starting point is that I'm working in an S-matrix theory of gravity. If tomorrow you come with a fully fledged quantum theory of gravity, which is not non-S-matrix, it's not based on that.
I'm not very dogmatic. I'll do almost anything to get the answer.
Yeah, very good. So then
really
let's
don't
not
understand what you're saying.
Sure, but let's not debate the starting point. I mean, how can you? I mean, this is my starting point.
I'm not debating. I'm pleading for clarification.
No, Andre,
I don't understand what you're saying.
Why every background should be constructed out of quanta defined on top of flat spacetime?
Because flat spacetime
I know that you like to do it, but that's not the only possibility.
Because the flat spacetime. No, I'm answering your question. Because flat spacetime, Minkowski space, is the S-matrix vacuum, and the Sitter spacetime is not an S-matrix vacuum. Therefore, it's not a vacuum for any S-matrix theory of gravity. Since I'm starting with an S-matrix theory of gravity, this theory is telling me.
Actually, I think the same concerns any other FRW metric, not necessarily.
No, asymptotically, asymptotically. The ones that slope asymptotically to Minkowski, there is no problem. There is no problem because FRW itself is an excited state that you can treat there. There is no problem with that. Andre, I'm answering your question. So.
But the place or the time where we live in FRW, it does not asymptotes to flat space time. We are just somewhere in the middle, and still we can do everything here.
Well, I'm giving a prediction. Can I get, so look, how physics works. Physics works in the following way. I take a starting point. Starting point, we cannot debate. I'm taking starting point, I'm saying, because that's my starting point. I want to work in an S-matrix theory of gravity, that I have a right to do that. Okay, I'm starting with that, and then I see what I get. Okay,
but I think that this is a very restricted approach in the scope. Not all the problems can be reduced to S-matrix ones. Don't you think so?
I like it. Yeah, I like it. I think that that's the only existing one so far. I think that's the fact of the state of art, that only formulation of quantum gravity in which we can do some reliable computations is the S-matrix computation, is S-matrix formulation. But let's not debate about the taste, because starting point is the starting point. Now, what I'm saying, what is important is whether this starting point allows me to compute and make predictions. This is the important thing, okay? I'm saying this starting point tells me that I have to always treat as a vacuum only a vacuum which is a S-matrix vacuum. Such is Minkowski. There is also ADS. We can treat it through ADS CFT, but let me not enter there. Let me take Minkowski as an S-matrix vacuum. Everything else is like a theater. Now you have a vacuum, and all the quantum drama that is going on in this theater is a stage, is Minkowski vacuum, okay? Now, in this approach, I can do computations, and I can derive certain predictions. And my prediction is that lambda cannot exist in such a theory. Lambda has to be exactly zero. I mean, it cannot be positive. You cannot have, you cannot have such a theory with a positive lambda. Also, I know that de Sitter can only last certain finite time, which is quantum break time. For example, eternal inflation is also out in this type of approach, okay? Now, of course, you have to do cross-checks.
The end of inflation, you mean eternal inflation?
Yeah, eternal inflation, right. There is a bound on the number of e-foldings, inflationary e-foldings in this approach. So now, usually when I'm developing some approach, what I need to do, I need to reproduce everything that is well established. For example, I can reproduce Alexei's tensor mode in this approach. I see that Alexei's tensor mode is a Hamiltonian process of decay of the de Sitter coherent state. And on short time scales, I'm reproducing exactly what he sees. But what I see that his picture is incomplete on long time scales. And so I can make predictions on long time scales.
Well,
so
but
that's
maybe
what I'm trying to say.
Incomplete in the framework of your axioms, because your starting point. So I think I heard your starting point. Do you want to hear my starting point, for example?
No, I don't want to hear it. No,
I don't want to hear.
Okay, let's maybe hear Alexei's starting point. Okay.
I don't want to hear it.
Please, let's hear Alexei's starting point then. Please, Alexei.
Okay, it's me. Okay, so let me point in which points I agree with Guy and in which points I agree. I agree with him in the sense that de Sitter is not a vacuum, but from a completely different reason. Because for me, the Sitter state is only one processable, is only one possible solution between infinite number of solutions having locally de Sitter asymptotics. And so locally the behavior is the same as in the de Sitter, but globally it's completely different. So for this reason, for me, it's even so once more, I'm using the classical picture, a classical picture of what happens in the Einstein gravity plus a constant lambda. But once more, simply from the fact that late time generic asymptotic in this classical theory is so complicated, I cannot understand how in quantum theory this model may have a unique vacuum. Okay, and then another I prefer with gear in this model. Once more, I don't worry that Einstein gravity plus exact cosmological constant doesn't have, I would say, exact mathematics. It has approximate.
No, that's not true. No, that's not true. I'll explain it.
Absolutely.
Once more, in particular in inflationary models, we never, in contrast, what is often said, we never use the so-called exact initial tether for exact initial how it's called.
No, with that I agree. With that I agree, Alexei. No, I don't think we contradict in that.
Okay.
In real life, NS matrix is just approximate.
Let me end. So my statement is that in this restricted approach, I can investigate what that happens at arbitrary late time, and the difference is that this de Sitter will be this locally de Sitter. So globally it's not de Sitter at all. It will be filled by gravitational waves, but not in the coherent state, but in the extremely squeezed state. It just is what happened in the case of all perturbations generated in the cause of inflation.
No, let's not confuse coherent state of what has been produced. I'm not talking about that. I'm talking about de Sitter itself as a coherent state. So let's not confuse the two notions. I'm not talking about fluctuations as a coherent state. That's a different story.
I think that the principal difference is that once more, de Sitter, what happens with the de Sitter in the case of exact cosmological constant is that it transforms into something, as I said, filled by extremely squeezed quantum states of gravitons. And
Alexei, as far as semi-classical picture is concerned, you and me 100% agree with each other. We teach, I don't know, I teach students exactly what you're saying. That's not the, I'm not saying that semi-classical picture has no domain of validity. That would be completely crazy to say. Of course, semi-classical picture has domain of validity, but there is physics beyond that domain. Now, where does that domain happen? Precisely that happens where you want to cover the global structure of the system. This is what the symmetrics theory tells me, that precisely this domain of validity of semi-classical gravity, or semi-classical de Sitter, breaks down beyond that, precisely where the global structure becomes important. You cannot turn it around and use these arguments against this matrix. That doesn't make any sense. Because this matrix theory is more fundamental than semi-classical theory.
Once more, my comment is that what I can say, what happens is with the de Sitter, okay.
What I'm saying is that you cannot rule out more fundamental description by less fundamental,
of course,
as long as more fundamental reproduces what is known in the less fundamental description.
So what is more fundamental? Description in terms of S matrix, or say description in terms of setup in the finite time duration, finite time quantum transition in finite time. I think this is more fundamental than just S matrix, because S matrix, this is just the limit.
Andrei, you will not succeed in taking me away from my point, okay? Don't try to take me away somewhere else, okay?
Let's see the point here.
I'm making a very concrete point, and I want to stay there. I don't want to go into some other descriptions.
I think there is Philip who raised his hand like a while ago, maybe.
Right.
But everybody wants to do the same, I would say.
Okay,
please, Philip.
May I briefly raise a point? I also want to do the same as Alexei and Gia, but I have a problem with Gia's starting point, which is that you have an S matrix in string theory. But if you have a universe without boundary and there are particles everywhere, which I don't believe they are in a coherent state, but there are planets and stars with life on them and so on.
No, of course they are not.
So,
I mean, obviously,
so you don't have really an asymptotic state. It's
rather better FRW is a coherent state.
That you can work with an S matrix with a finite number of particles in, and the finite number of particles out, that would be a nice S matrix. That's the kind of thing you want to use in string theory, but that's not our universe. So you have to make some approximations. But a very wise thing to do, of course, is to say, well, let's idealize situation. Let's consider a region of space-time that happens to be empty for some reason, and then ask what happens if I put a finite number of particles in. That's fine. And then you have your problem that there is a cosmological constant lurking in the background. The cosmological constant seems to be being canceled out in a space-like direction by matter. And that's very convenient because at least space looks more or less flat, and the curvature is only in the time direction. That will be fine. But still, you can't, in principle, you can't formulate all that in terms of S matrices. What you have to do is probably have to look at an evolution operator. So you have Cauchy surfaces, and the Cauchy surface propagates from the past to the future. And you have evolution equations to tell you how it does it. That's a lot harder than an S matrix.
Yeah.
So,
Gerald,
of course, you all agree you have to start somewhere.
These are, of course,
at some point,
this is, of course, a very important question. Yes. No, what you're asking is precisely important question, a very important question, and I would love to answer it in more details, but just very briefly. So again, look, the point is the following. What I'm saying is that I have a starting point. I know how my theory is formulated. First of all, I never said that FRW and our planets are coherent states. And also, coherent state itself is not so important. What is important that everything should be an excited state on top of a S-matrix vacuum. But what I'm saying is the following. I'm saying that I know this description of gravity. Then I'm just following what this description tells me. I cannot come back and change theory every time I don't like something. That's not my approach. I'm saying theory tells me that it has to be formulated through the S-matrix. Let me stick to it. Then I cannot touch it anymore. I have to declare what the theory tells me. So then this theory tells me, formulated as an S-matrix, that lambda is inconsistent. It's like anomaly, right? The theory tells you through the consistency that lambda cannot be there because otherwise the theory is not consistent, period. Now, you want to now what you're saying, no, this cannot be the case. Therefore, you have to change your starting point. First of all, you don't know whether this cannot be the case. You don't know. You don't have any experimental evidence, nothing. You don't know whether there is lambda in the universe. Nobody told us. That's
what cosmologists are telling us.
No, they are telling us that the universe is accelerating. By the way, there are also some people even questioning even that, but I don't want to enter there. I'm not an observer. That's not my point. But what I'm saying is that there must be, in physics theory, the logic is you start with a theory, and then you derive whatever this theory tells you without every time try to modify the theory. Now, if the prediction is obviously wrong, for example, if this description would tell me that there are no tensor modes in the Sitter universe, I would throw it away because I trust Alexei's computation so much that I think any consistent theory of the Sitter should reproduce those tensor modes. But everything that we know is reproduced. The difference is in long time scales. At that point, I trust my computation because at that point, I think the fundamental theory is telling me something important. So that's my approach. So therefore, I cannot accept this point.
I personally think you have to think twice about your starting points. Maybe
that's different.
It could be not the ultimate theory of nature. I don't understand why people always think string theory is the end. String theory is an assumption, a starting point, something.
I think I made a mistake by mentioning string theory. My starting point was S-matrix theory of gravity. String theory is an example that I know works, and that's why I'm sort of normalizing things to string theory. But we don't have to mention string theory. My starting point is an S-matrix formulation of gravity. Now, Andrei said that approximate S-matrix formulation is still there. And this is an extremely important point why this is wrong. And let me explain why this is wrong. Because you see, if I take QCD in the Sitter, that's absolutely correct because I can use S-matrix approximation at shorter and shorter distances because QCD is an asymptotically free theory. It's Wilsonian. So in QCD, to probe very short distances, I can do experiments with higher and higher energies. Now, in the Sitter with quantum gravity, that doesn't work because of black holes. I cannot probe shorter and infinitely short distances with finite and Planck in the Sitter. Impossible to probe infinitely short distances. Inevitably, sooner or later, if you want to probe short distances, the center of mass energy of your particles that you have to scatter will exceed entire energy of your Hubble patch. And of course, as matrix computation is out of window. So that's the fundamental difference between gravity and Wilsonian interactions. That's why you can formulate those in de Sitter. There's absolutely no problem for scalar theory in de Sitter or QCD in de Sitter. But there is a fundamental problem with quantum gravity as matrix description in de Sitter. Because it doesn't
maybe be a fundamental problem with the S matrix. As I said, because there are no asymptotic states really in the universe. So you are doing approximation. It may be a very good approximation, but it's still an approximation.
No, but that starting point I cannot debate, Gerald, because maybe
Why
you are
not?
right.
I think you should debate.
You could be right. No, you could be right. Look, I may be wrong, and maybe there is a fundamental formulation of quantum gravity which doesn't need S matrix. Then, of course, everything I said should not be taken into account. I accept that.
The fundamental formulation of the degrees of freedom and the evolution laws of gravity. There's no doubt.
Yeah, if you have such a
the
formulation,
how do you do it? That's a very difficult question of strategy. And you are advancing one strategy, that's fine. I have nothing against it. But you should also consider the possibility that some other people want to use other strategies. Of course,
sure.
At the same point.
Okay,
no, Gerald, I fully agree with you. I'm extremely open-minded. I'm extremely open-minded. I'm willing to hear everyone. And by the way, that's why I'm attending this conference. I'm trying to hear all the talks because, of course, that's my approach. I mean, we have to try all possibilities. I don't want to be misunderstood in that direction.
I still don't understand how you want us to do calculations. Please tell me.
No, please, guys. I think there was Philip who had.
But what approaches do we have other than S matrix?
Please, Philip.
Maybe someone can tell us also.
I think Philip wants to say something. Philip, please.
Okay. So Philip, could you tell us what approaches do you have other than S matrix?
You are muted, Philip. Sorry. Philip, you are muted.
The problem with the S matrix has infinite things from the infinite past move to the infinite future. So you have to integrate over an infinite stretch of time before you can even compute the S matrix, strictly speaking. So it's going to be very, very hard. What we really want to know is not what happens at infinity, but what happens at very small scales. What are the fundamental degrees of freedom in a tiny fraction of the universe? And can we glue all these pieces of universe together some way or other to get the complete theory? Now,
that's why it's not
okay, so guys, Philip, please, let's leave some space to Philip.
Okay.
Philip, please. Yeah. He
was
the first one to raise the hand, I think, or the second. So please.
It's good to listen to everyone. I wanted to do two separate things. I want to ask some questions of Andre about this morning's talk, and then Luca asked us at some point in the discussion to respond to all the issues he raised in the summary, but I'd like to defer that for the moment and just deal with this morning's talk.
Yes.
And let me perhaps at the same time answer Richard. Yes, we are a minority, and Carl Bender and I are an even bigger minority, an even smaller minority within the minority. But all of us are in agreement that radiative corrections in a gravitational field generate higher derivative terms. And if the community wishes to ignore that, that doesn't stop it from being correct. And all of us are trying to deal with those terms. And now I can come to Andre. I don't really understand unimodular gravity, and I also have a question about Harava gravity, but let me do the unimodular first. You want to fix the determinant of the metric. Now, Harad has done a calculation, a path integral, where he uses the determinant of the metric as a degree of freedom. And when he integrates that up, he recovers fourth order gravity. So if there is to be a ghost problem, then it would seem that it is due to using the determinant of the metric as a degree of freedom. And I don't know that you can simply ignore it. Maybe you can say that the path integral over all the other degrees of freedom is okay. And I think that's what you're heading for. And if that's so, then at least Harad has diagnosed where the problem begins. But now how it affects you. I don't know how to say, keep the determinant of the metric equal to 1 unless I introduce a Lagrange multiplier for the determinant of the metric -1.
Absolutely, absolutely.
Yes, and then the Lagrange multiplier will replace the determinant of the metric in the path integral, and its integration will recover the problems that you were trying to avoid. It looks to me like that seems to be the strategy, what would happen. The second issue I wanted to raise is about Harada gravity. It looks to me as if once you do that, the canonical commutators are going to be non-local. And I don't know that you've discussed that or what it means, but it completely messes up all propagators. So I don't know that you can do these tricks of sort of putting phases on the spatial piece without messing up the canonical commutators of the theory in a rather violent way. So those are my concerns, not necessarily that you can't answer them.
Well, there are too many questions maybe. Okay, but I will try to at least separate them into two groups. First, with unimodular gravity, you see, fixing the unimodular gravity, you fix the determinant of the four-dimensional metric, which can be interpreted as expressing the, say, G00 or lapse function in terms of three metric. And this is one particular choice. You can generalize this to the relation which is more general, and in a sense this generalization leads exactly what you've said regarding the Lagrange multiplier contribution. You contribute your this constraint on metric with the Lagrange multiplier into the action, which is equivalent to just expressing one variable in terms of another. And then this term serves as an effective matter stress tensor. If you write down equations of motion for this system, you will get usual Einstein tensor on the left-hand side and this source on the right-hand side, and this source will have the structure of perfect fluid. Lagrangian multiplier will play the role of this dark fluid, so to say. And that's the picture. So I don't know whether I have replied to your question, but this is the idea. You take the Lagrangian, in which you either express one variable in terms of another, or you add this constraint with the Lagrange multiplier.
Well, not quite what I asked, but I was going to put the Lagrange multiplier into the path integral measure, not just into the path integral action, because you've turned it into a new dynamical degree of freedom, and therefore you have to do a path integration over whatever the degrees of freedom.
Okay, but then of course you start canonically quantizing this system, and there is nothing special. This is just a typical procedure. First you build canonical formalism, and then perform Dirac quantization.
Yes, but you're going to go off paths in which the determinant is one. That's what I mean. There are other paths in the path integral that you have to include. That's my concern.
Well, there is nothing special about the determinant of some matrix or metric, whatever. This is the same for any type of restricting your phase space or configuration space of the system. You kinematically restrict your configuration space, then express it in terms of independent variables, and write down the path integral in terms of this independent variables.
I think we're agreeing on that. You can certainly restrict the space, and the only issue is in that restriction, have you actually got rid of the ghost? I mean that's basically the asking.
This is just a technical procedure. You write down the resulting action, you consider the quadratic form, and then you analyze the wave equation for this quadratic form, for the quadratic part of the Lagrangian on a given background. Of course, this is background dependence problem.
Okay, I would say.
Of course, this means that, for example, if you have a ghost, then this means that this background is not stable under the back reaction of this ghost modes. That's the picture.
Okay, I think this technical point can be also further discussed privately, maybe. I think there was also Nikolai, and there was.
I would like to. Do you hear me?
Yes.
Do you hear me?
Yes.
I would like to ask Andrei Barvinsky. I have, in fact, the two questions. The first one, when you couple gravity in Harava model with matter, say with electromagnetic field, you also violate Lorentz invariance. It's the first one. And the second question is, what about experimental bounds? Because I guess in this case, in your theory, experimental bounds will be very untrivial. Thank you.
Well, of course, well, if you couple this gravity model to usual matter, then of course this violation of Lorentz invariance, it will of course penetrate through all the physics. And so the only hope to match it with what we have in nature is to suppose that at certain energy scales, this Lorentz violation goes away. That's the picture. And this part has not been implemented at what I suggested, of course. So this is a matter of hypothetically, this should look like that these quantum renormalization group flows should bring us to the situation when you recover in a certain energy limit, you recover just usual general relativity or just unimodular gravity. Unimodular gravity is basically equivalent to Einstein's theory, modulo the fact that the cosmological constant there becomes just a part of initial conditions. Or you can treat actually unimodular gravity as Einstein's theory in a particular coordinate gauge. Now, the second part of your question was about what?
What about experimental bounds?
Well, experimental bounds the situation is the following: that every solution of this generalized unimodular gravity is also a solution of Einstein general relativity with matter. So in this sense, of course, there are additional degrees of freedom which can spoil this harmony. Frankly speaking, I don't think that I have a ready answer to your question regarding this good experimental bounds. Well, it will take me some time for me to sort it out.
Okay, so I think we can maybe close the discussion related to the three, four talks of today, and we can just leave some space to John Donog and Philippe who want to say something about the first session and some of the points that were raised. So I would say let's just leave some space to them to speak without any interruption, okay, for like, I don't know, for the time that is needed. Then we stop it and we delay slightly the start of the second session, okay? So please, John, maybe you want to start.
So you want to do that now?
Sorry?
You want to do that now?
If you are okay, yes.
Okay, good.
Yes,
so
sure.
I appreciated the summary of the first day's discussion because it makes a fixed set of comments that is not associated with the back and forth that we get in person. But I'd like to make 3 points, and I'd like to, as I said, do it without interruption, and we can talk after if we want. The first thing is I think I'm speaking mostly for the quadratic gravity folks, but they can chime in. I'd like to state unambiguously that the states that we're discussing, these ghost states, are positive energy states. It takes positive energy to produce one. It takes twice as much energy to produce two. To produce two plus a normal particle takes yet more energy. All the quantization schemes and also the path integral have that feature. It's all the way back to Lee Wick. So there's no runaway solutions from producing one of these as a negative energy particle. They're all positive energy. The second comment is that Oster-Gradsky is likely irrelevant. It's a classical theorem. It's likely not true in these quantum frameworks that we're discussing. And it's partially because of this. The first point is that these quantization schemes have changed the spectrum in a way that the classical theory doesn't know about. And it has made these things into positive energy particles. And so saying Oster-Gradsky is probably not a useful thing at low energies. It's like saying the Dirac equation can't be true because it has negative energy solutions. Quantization has changed that. The third thing is that the classical limit of these theories is not classical quadratic gravity. It's actually Einstein gravity. The classical limit is the low energy, low curvature version of the theory. The high energy and high curvature is intrinsically quantum. And in that case, there's no differential equations, there's no effective metrics, there's no geodesics. You think more like in lattice theories where you can do correlation functions, or like causal dynamical triangulation does the effective dimension of space-time. But it's not, there's no classical limit in those cases. And I know how to take the low energy, low curvature limit of these theories, and that leads me to the effective field theory. And the classical limit of the effective field theory is Einstein gravity. So that's how all these will limit to Einstein gravity, not to quadratic gravity at low energies. So I think these are not the main issues. I mean, I think the theory does have issues. Gief pointed out a very important one, the Scheel and Lyman representation of propagators and correlation functions. Those are given to us by axiomatic field theorists, and those are then axioms for God's sake. If we're violating some of those, so we're violating some of the axioms of field theory. So we have issues we have to deal with, but I don't think the positive energy or the classical limit are the important issues. So that was my statement. Thank you.
Okay, thanks. So I would avoid further question. We can postpone them to the final day, okay, for further discussion. But Philip, maybe you want to say something too, right?
May I make a short comment? That's
well, if he's very short, yes, because otherwise
in my talk I was explaining that it's not the energy of the. I mean, if you look at the propagator for the graviton, you get this extra massive piece. The energy is positive there, but the metric is negative, and that's just about as bad. So
I argued in the talk. I'm happy to argue about that part. That part is an issue, but I argued in my talk that we maintained unitarity despite that minus sign. That the propagators are time reverse propagators rather than negative energy, and that is an issue. Yes, let's discuss that part.
It's a negative sign in front of that propagator, which is a problem. In ordinary field theories it is. In the standard model, that sign was removed in a clever way, such as now the model works, and it agrees with nature. So there may be good reasons to say, watch out for those negative metric signs. It's likely that something has to change in those theories.
Okay.
Well, I made my argument that it does not change unitarity, but it does change causality. So that was the. And so, yes, it changes something. It changes the causal structures. If you think that that's a total failure, then we should move on. But I'm prepared to explore further the unitary but non-causal
we all agree that we should study this, but as situation is now, having no answer is not good enough. Someone has to explain that minus sign in a logical way. I mean, it's forbidden in ordinary field theories. For some reason in gravity, it seems to be compulsory instead of forbidden. We want to understand why that is and how that doesn't make the theory inconsistent by itself.
Okay, maybe we can go to Philip. Yeah, Philip, please. With no interruption, please. Yeah.
No, I'm on. I'm live?
Yes, you're
Yes.
there. Yeah, you're with us. You're with us.
Endorse what John said about negative energies and negative norms. When this discussion I gave of the Pais-Uhlenbeck theory was you could define a Hilbert space where A annihilates the vacuum, or one where a dagger annihilates the vacuum. In the one where a dagger annihilates the vacuum, you can guess, that sounds like negative energies running forward in time. So that's the one which has the negative energy problem. The one where A annihilates the vacuum has the ghost question, but there's no Hilbert space in which you have both. So you either live in one Hilbert space or the other. The one where a dagger annihilates the vacuum is the one that would link into the classical Ostrogrodsky problem, because there you are working with a Hilbert space that has the same problems as the Ostrogrodsky classical space. However, if you live in the space that A annihilates the vacuum, then that theory is a well-defined quantum theory, and it doesn't really matter that you don't reach the classical Ostrogrodsky case. That's the theory that you work with, and whatever its classical limit is, its classical limit is. And the fact that it's not Ostrogrodsky does not mean that therefore there's something wrong with it. We're used to the idea that fermions are intrinsically quantum mechanical, and we live in a Hilbert space, we don't live in a classical space. So now we have to go back to the question of the ghost, because that's the one we have to live with, and that's the one that we encounter in every single place. And the ghost is simply the statement that when you calculate an inner product, you require the bra to be the Hermitian conjugate of the ket. But that's not required by any law of nature. What's required is you have to construct the Hilbert space, you have to construct the dual space, and Carl Bender and I are stating that when we do that, we find that the bra is the CPT conjugate of the ket and not the Hermitian conjugate, and then we have a positive definite inner product. Now, for every other theory that we've dealt with, the Hermitian conjugate and the CPT conjugate have coincided. So our whole familiarity with looking at inner products is to think in terms of Hermitian inner products, and the fact that they come out negative is not telling you the theory is sick, it's telling you you're in the wrong Hilbert space. And that's the position that we are promoting.
You do want to understand how unitarity works to produce positive probabilities. We cannot accept a theory that tells you that the probability of producing such a particle is minus so and so. That's not a consistent theory. So something has to be done about it. I'm not saying it's wrong, but it says you need further explanations as to why that is allowed and what it really tells us about nature.
Yes. Okay. So let me proceed to the unitarity question. So it turns out that the conjugate of the ket is the left eigenstate of the Hamiltonian, and the inner product is the overlap of a left vacuum with a right vacuum and a left eigenstate with a right eigenstate.
But how do you tell an experimentalist to look at the left eigenvalue, at the right eigenvalue, at the bra or at the ket? No, the experimentalist just looks at particles and measures probabilities, and those have to be.
I'm coming to that. So now, we've got to construct the S matrix, and the operator, which is the evolution operator in time, is usually written as the sum on right ket, right bra. And that's the one which was going to give you loss of probability in these fourth order theories. But there's another choice, which is the one we take, which is right ket left bra. And that one gives you a positive definite probability. And that's the one that we've worked through.
You know, if you replace squares by products of two things, then you also lose unitarity. You also get minus signs all over the place.
No.
Watch out what you're doing.
Okay, sorry, Philip.
The unitarity in this theory is not S dagger equals I.
Then what is it?
What it is there's an operator V that takes you from left to right, and what you get is S V S dagger V to minus 1 is equal to I.
And how do you tell an experimentalist to check that? This is not physical information that you're giving us. There's some mathematical trick that you think works, but it sounds all wrong.
Okay, let me say the following. You now do two-body to two-body scattering, and you have a loop. Let's just do one loop. If you calculate that as is, with the usual Dirac norm, you will find that the discontinuity across that graph is negative. So when an experimentalist measuring two-body scattering would curiously receive a negative discontinuity. And of course, that's not what they would measure. However, that's not the whole story. There's another contribution coming from the tree approximation, which is totally absent in standard theory, but will appear, and it cancels the discontinuity. And when you're through, what the experimentalist measures is, in lowest order, modulus squared of tree plus one loop is a perfectly normal positive definite cross-section. And that's the cross-section that you would get if you did graviton.
May I say it this way? You know, I'm not totally disagreeing with you. You may be right, but I want to understand how it goes. The experimentalist measures the probability that two gravitons are produced, but then the theory tells us he has to subtract from that the probability that a single heavy particle is being produced.
Oh,
now,
no.
What is he producing?
Okay, I'm saying that you measure the two-body to two-body, and you'll get a normal answer. The same as you would do body to two-body.
You get the answer that two gravitons may be produced, but you have to remove from that expression the probability that a single graviton, massive graviton, is being produced. And that's a very strange thing to tell to the experimentalist.
Okay, now I have to back up a second. Okay. If you want to discuss second plus fourth, while you have everybody positive norm, there are additional states, and John has talked about those. However, if you want to stay with C squared, that's pure fourth. And then the spectrum of states is completely different. And I mentioned it very quickly on Monday, then the Hamiltonian is not even diagonalizable anymore. And what you find is that the gravitons that are in the theory have zero norm. So it looks to me that in this theory that gravitons are not going to be observed. Now you're going to jump on me, but we've seen gravity waves, and I'm not disputing that. But that doesn't mean that when you quantize them, that you necessarily get observable particles. And
I think this is a question about very high energies. So the gravitational waves that are being observed are very, very low energies in that notation. So I don't think there's any conflict.
Yes, okay. Anyway, so what I'm saying is that we run into a whole new set of problems if we go to pure fourth. I mean, everybody in this workshop has been working on handling second plus fourth, and John has explained how that theory's classical limit comes back to standard Einstein, even though he's in this very different Hilbert space than the one that would have got you to the Ostrogrodsky, which is excellent. But there's a whole different theory, which is the one which is pure fourth. And the whole Hilbert space structure of pure fourth doesn't link on at all to the Hilbert space of second plus fourth. But nonetheless, what I was describing to you initially about scalar products was in reference to second plus fourth, where you have 1 over k squared minus 1 over k squared plus m squared. But if you wanted to take the limit m goes to 0, that partial fraction decomposition has to be multiplied by another 1 over m squared, and that makes the limit singular. And the singularity results in a Hamiltonian that's not even diagonalizable. And we have very little experience with that, but Carl Bender and I explored how such a theory could be unitary. And I'm going to tell you the answer.
The reason why we don't.
Okay, sorry guys. So I think, yeah, we are really, look, Alberto, please, 2-3 minutes for you, and then we'll take a break before the second session, which anyway will be about ghosts and how to solve the ghost problem with nonlocal theory. So anyway, we can discuss again also about other approaches in comparison with the nonlocal theory. So please try to be there also in the second session. We can keep going also after in the discussion session. So Alberto, please.
Okay, so I just wanted to answer your questions that you put in the summary. And by the way, thank you very much for the summary. So regarding the first question, so this is a question again about possible instabilities due to producing this massive spin 2 particle through the decay of something else. In this case is the inflaton. So the answer to this question is similar to what John said at some point before, that I use a positive energy quantization. So this inflaton decays to positive energy quanta. So in this sense, there cannot be any instability. So this is the answer to the first question. And regarding the second question, which is more a comment, regarding black holes. So actually, I never said that it's clear to me that the horizon never appear in the theory. What I said is that I know that for a very small Schwarzschild radius, the horizon does not appear. And I said also, I don't know if there are macroscopic black holes in the theory, although I expect that there aren't any, because essentially the known solutions for extended matter sources are without horizons. This will be, for example, discussed by Bob Holdom talk soon. So the reason is that since gravity is softened above some energy scale, then I cannot see how you can shrink a matter distribution up to a point, as it happens, for example, in GR, because in GR, the strength of gravitational interactions increase with energy, so it becomes bigger at smaller and smaller distances, and so you can have this collapse up to a point, while in this softened gravity theory, at some point the collapse should stop because gravity becomes very, very weak. Okay, that's all I wanted to say.
No, I think, yeah, the second point can be also further discussed tomorrow in the second session. If you're also there, we can also take this point again. Okay, also with Bob Holder. Would be very nice. Thanks, Alberto.
I think the first point will
elaborated
in the cosmology session.
Sorry, I thought you wanted to reply. Okay, no.
no, I'm not saying now.
Okay,
in the cosmology
so
session,
let's thank all the speakers of the previous sessions, I would say, also of the previous days. And let's just have 7 minutes break and we start again, actually 6 minutes break. Okay, so see you soon.